One of the important uses of transistors in electronic circuits is as an amplifier, though there are other uses like in switching, oscillators, and frequency changers. Amplifiers are devices which can amplify weak signals and make them strong signals. Different types of amplifiers are used in radios and audio devices. Amplifiers used to amplify very weak signals and provide a drive to power amplifiers are known as preamplifiers. Power amplifiers are the output stages which provide large audio or radio frequency signal outputs. Power amplifiers are classified into Class A, B, AB and C amplifiers, depending on the region of the characteristic curve of the transistors at which they operate. Each type has a different application in electronics. While these classes are for linear amplifiers, there are also Class D and E for switching designs. Classification of the linear designs are based on the time period during which the active amplifier device is passing current, expressed as a fraction of the period of a signal waveform at the input. This metric is known as the conduction angle theta. Class A amplifier conducts through the entire period of the signal and has a conduction angle of 360 degrees. Class B amplifiers conduct only for half of the input period and have conduction angle of 180 degrees. Conduction angle of Class C amplifier is less than half that of the input period and is less than 180 degrees. Conduction angle has relation to the power efficiency of the amplifier. Transistors biased for Class A amplification drain current continuously and their efficiency is poor. Heat is generated in the transistor. Class A amplifier needs only a single transistor, while Class AB requires two transistors. Bias is in such a way that the transistor operates at the most linear portion of its transconductance curve. Transconductance is the relation between current through the output of the device and the voltage across the input of the device. As the device is always on, there is no turn on time and generally has better high frequency performance and feedback loop stability. Fewer higher order harmonics are generated. Class A amplifiers are best for radio receivers with low signal levels and low distortion. Due to poor efficiency, typically only 25%, current consumption is more. If higher output is needed, power supply becomes larger, more expensive, and heat sinks are needed. Class B amplifier conducts only for half of the cycle. As only half of the waveform is amplified, significant harmonic distortion is present in the output signal. In case of radio frequency amplifiers, this is taken care of by using tuned circuits in the output so that harmonics are shorted to the ground. This configuration is often used in linear amplifiers. At audio frequencies, two transistors can be used in a push-pull configuration. Each transistor conducts for one half of the signal cycle and the outputs are combined so that the load current is continuous. Class B amplifiers have a higher efficiency at around 60% as current wastage is lower. They are favored in battery operated devices like transistor radios. There is some distortion at the crossover point as one device has to take over supplying power exactly as the other finishes. This is known as crossover distortion. Class AB amplifier is intermediate between Class A and B in that conduction angle theta is more than 180 degrees, so that each of the two active elements conducts a little more than half of the time of a signal cycle, so that the crossover distortion mentioned in the case of Class B amplifiers is minimized. It is also possible to further reduce crossover distortion by using negative feedback. In Class AB, the amplifier conducts a little more than half into a small part of the second half of the signal cycle. Hence, region where both devices will be simultaneously nearly off is reduced. When waveforms of the two devices are combined, crossover distortion is greatly minimized or eliminated. As there is a risk of thermal runaway damage to the devices, bias voltage has to be adjusted according to the temperature of the output transistors. Diodes shown in the circuit will be mounted close to the output transistors and will have a matched temperature coefficient for this purpose. Compared to Class B, there is some decrease in efficiency in order to improve linearity of the Class AB amplifier. Still, it is more efficient than a Class A amplifier. Conduction angle of Class C amplifier is less than 180 degrees, meaning that less than half of the input signal is used. This leads to high distortion and requires a tuned circuit as load. It is suitable for radio frequency transmitters operating at a single fixed frequency. Efficiency is as high as 80% in such radio frequency applications. Diagram shows the output waveform in the absence of a tuned circuit. When a tuned circuit is used in the output, it restores the waveform to its proper shape. The resistor shown in the diagram is replaced by a parallel tuned inductor-capacitor combination which resonates at the operating frequency. Power transfer from the inductor can be done using a secondary coil wound on the inductor. Average voltage at the collector is equal to the supply voltage, and variation in signal voltage can be between 0 and twice the supply voltage during the radio frequency signal cycle. Bias voltage of the transistor is adjusted so that it conducts only for about 1/3 of the radio frequency cycle, 120 degrees or less.